Is that okay?
Yeah.
Cool.
So I think we can start. We welcome our today's speaker, Cliff Cheung from the Caltech. And Cliff will tell us about a quickly growing and very interesting topic, which is basically what we can learn from color kinematic duality. Please, Cliff.
Okay, great. Well, before I start, let me first thank Alessandro and Roberto for inviting me to speak here today. It's great to be here, even if it is in a kind of purely virtual capacity. So I was asked to talk about scattering amplitudes, and I'm going to do that. And there was a request to kind of not just kind of recap the many kind of technical achievements and developments that have happened in recent years, but also to kind of ground those developments in the maybe bigger question of how this all fits into what it's taught us about quantum field theory in general. Okay, in particular, maybe with a viewpoint of trying to explain this to people who don't work on amplitudes in a kind of day-to-day activity. So I'm going to try to do that. In particular, emphasizing my view, which is that I believe that scattering amplitudes have offered a window into finding and discovering new structures in QFT, and that these structures in QFT can be studied with amplitudes, but I think can also be understood in general ways using standard methods of symmetry and quantum field theory and actions, and that these are all kind of all together a program to understand better quantum field theory. So my talk will be kind of split into two parts. The longer first part will be about kind of some new structures that have been understood from the point of view of amplitudes and how they connect to the bigger picture. And then the kind of last part will be about how these kind of amplitudes technology has been used for a new kind of phenomenological problem, which is the binary in-spiral problem, which is relevant to gravitational wave physics at LIGO. Okay, where there's been a lot of recent progress in the last couple of years. So just to kind of zoom out, the big picture. The big picture is that the kind of standard way that we study physics in high energy is we start with some theory, which is almost always defined as a Lagrangian or a Hamiltonian or something similar. That's like our starting point, and then we compute everything else from it, which include things like amplitudes or let's say correlation functions and so on. And the amplitudes are like the observables. They're kind of a means to getting to connecting to data, and that's a perfectly fine and reasonable thing to do. Of course, when we define the theory, we have to input some set of principles, and I call these kind of basic cherished principles like Poincare invariance or locality or unitarity, things that I would say are well established experimentally, and that's why we kind of put them up on this pedestal of being principles. We can also add things that are not strictly speaking required by consistency, but have strong motivations like supersymmetry or extra dimensions. I call these luxuries just because they're not 100% required, but we can add them and we'd like them if we want them. Now, if you've seen any talk on amplitudes, you know the idea of the scattering amplitudes program is to reverse this logical flow, which is to say, to start from the amplitudes, input all those principles or luxuries or what have you into the amplitudes directly, and use this to understand the action or the theory in general. Okay, and there's no kind of free lunch here. Okay, the things that go into Lagrangians are those fundamental principles. We bake them into the action directly, but instead of doing that, we bake them into scattering amplitudes. So the kind of general workflow for the amplitudes program is you write down a space of functions which can be the amplitude. So these functions depend on kinematic invariants that are defined by the problem that you care about. You have in this space of functions free parameters. You constrain those free parameters by those principles that you impose, and then you just ask what comes out. And the things that come out are the S matrices for theories. Okay? Now, immediately you should ask, what is the purpose of doing this? Because this seems a little bit like a gingerbread house, right? It's like you could do this in this kind of funny way, but what can you learn, especially if you're working in perturbatively, which is everything we'll be considering. Everything perturbative you can compute using a Lagrangian and Feynman diagram. So what do you actually win, which is what I want to first discuss. What is the benefit of doing this? And really, one issue is the deficiency of the kind of standard way we do things. Obviously, the standard way we do things has a lot of positives, But there is one deficiency, which is, ironically, in terms of calculation, the existence of gauge symmetry. So why do we need gauge symmetry? Of course, we know gauge symmetry exists essentially because we're very greedy as physicists. We know that the final answer depends or is explicitly Poincare invariant and local and has all these nice properties, but we don't just want the final answer to have that property. We want every single step of the calculation to have that property also. So what we do is we build a formalism where Poincare invariance and locality are just hard-coded at the very start. For instance, with an action, which is Poincare invariant and given by a local integral over space-time. But then, of course, we have too many degrees of freedom when we introduce higher spin fields. So we have to invent a gauge symmetry to reduce that number of degrees of freedom down to the two helicities, say, for massless spin 1 or massless spin 2. Now, the downside is that we then have ward identities, which then relate terms when we compute scattering amplitudes. So if you've seen any talk on amplitudes, I'm sure you've heard the story, but I'll repeat it here. You could compute, for instance, the 5 gluon scattering amplitude just using standard Feynman diagrams. And this is the expression here. So I don't know if you can see this blob, but it's roughly 300 terms, all made up of complicated products, ratios, and sums of polarization vectors and momentum vectors. And that's just the right answer in the kind of standard textbook formulation. But of course, we know that if we restrict to on-shell kinematics, physical kinematics, which maintain momentum conservation and the helicities of the external states, then we get these beautiful helicity amplitudes, many of which are 0, and the only non-zero ones are these so-called maximally helicity violating scattering amplitudes. And this is written in terms of spinor helicity variables, which I won't go into deeply here, but just a compact re-expression of the usual momentum variables we're used to. Now, the bottom line here is that the final answer is super simple. It's elegantly simple. The intermediate step is extremely complicated, and it strongly suggests that there is something missing in the way we usually compute. There should be some theory that directly computes these. Okay? And the idea that you might exploit that is not an abstraction. I mean, kind of famously, when Park and Taylor wrote down this formula, they, of course, knew that this was beautiful and something kind of deep was happening. Other very insightful and smart characters like VP Nair saw this and immediately said, these MHV amplitudes are actually correlation functions in the 2D theory, 2D conformal field theory, and then thought about the implications of that. Later on, Ed Witten, Andy Strominger, others found other ways of understanding these types of formulas through either the twistor string or through celestial conformal field theory at asymptotia. But the kind of point is, with enough insight and given a beautiful formula, it can be, there can be times where you're able to actually breathe like life into these equations that has a different origin story than the one we're used to. Okay, now, this is not just a property of spin 1, of course, spin 2, that is to say graviton scattering amplitude has the exact same problem. This is the 3 graviton vertex, the 4 graviton vertex written down by DeWitt and Feynman ages ago. It's not surprising that if you take these vertices, build a 4-point Feynman diagram expression for the graviton scattering amplitude, it's a giant, it's like a megabyte or something. But of course, if you reduce to on-shell kinematics, you get these beautiful, simple expressions. Okay? So maybe not surprisingly, gravity has the same issue. Now, that might maybe naively suggest to you that this is all an issue of spin, but that's not the case. This intrinsic redundancy is really a property of QFTs, which you can see in the case of scalars, which are not even safe. So here's a kind of a particularly perverted example, which I like to present, which is consider this action, d phi squared times some function g phi, where g of phi is any function which has a Taylor expansion around about phi equals 0. Okay, so it's regular at phi equals 0. But otherwise, G is completely unfixed. It's basically a series of higher dimension operator coefficients that are completely arbitrary and have absolutely no connections between them. Now, you give this to a graduate student to study, and you tell them to compute the on-shell amplitude at 3 point, 4 point, 5 point, and so on. You'll find, to their chagrin, that these all vanish. Okay? And the way they vanish is kind of amazing if you do this, which is that it requires summing all the topologies and consistently adding them with all the right factors and symmetries and so on. Okay, so you have to do the calculation exactly right, and only when you sum everything together and go on shell will you find that there's 0. Okay, so this is like a little confusion, but of course, if we know anything about field theory, we realize that there's these well-known reparameterization theorems, so-called Haag's theorem, which allows us to do a field redefinition to map this action into the action for a free scalar. Okay. So, okay, and then of course some regularity constraints on F, which require it to not modify the asymptotic states, so on and so forth. But the bottom line here is that field redefinitions are a non-symmetry of the action. That is to say, something which changes the action, but nevertheless leaves the S matrix invariant. Okay, and what that means is that there's nothing intrinsically special about the action, because I can perform one of these and the physics remains exactly the same. This is something super familiar for, I'm sure, many of you who've studied the standard model effective field theory, where there are these, whatever, 59 dimension 6 baryon preserving operators in the SMEFT. And you can, of course, reshuffle them into other operators using equations of motion or equivalently field redefinitions, but there's no like right way to do it. It's just an ambiguity, which of course evaporates when you study actual physical processes, right? Now, of course, that ambiguity can be useful sometimes, but it can also obscure things. Now, this may seem strange in the context of QFT that a non-symmetry leaves physics invariant. We're of course super used to it in terms of classical physics, right? I can give you an action in Cartesian coordinates and I can do a transformation on it that changes the action. And that transformation is to go from Cartesian to polar. And the action is different, but of course, if you look at any physical observable, it's the same, okay? Assuming you properly mapped variables to variables and what you're actually observing, okay? Said another way, quantum fields are just integration variables in the path integral, and you can change variables, and if you're careful with how you change variables, you'll just get the same answer because it's a coordinatization of your field space, and there's nothing intrinsically special about it per se. Now, what's the downside of this? The downside is that if I give you, let's say, some action, this is the action that was handed to you in a textbook, L1, then I can apply a field redefinition to go to any number of other actions. In fact, I have infinite freedom to apply any field redefinition. In addition, I have any gauge fixing, if you like, if you have a theory with a gauge symmetry. And it gives you a whole class of Lagrangians, an infinite class, which all point to the exact same scattering amplitude and are all equivalent physically. Now, what's the downside? The downside is, well, maybe you were lucky enough to have been given L1, which has every possible structure and symmetry of these theories just built right into it. It's all just plainly there. But there is a chance that there are structures that exist in quantum field theory that are simply not manifest in the way we describe them, right? The obvious example being unitarity in the case of studying Lagrangians. Now, of course, you could take your given action and just kind of methodically study every possible field basis transformation of it and hunt for structures. But there's a much more direct path, which is for this type of question, just go directly to the amplitude. The amplitude has modded out all these ambiguities, and you can just study it and look for the structure and then ask what that structure means, even if you like at the Lagrangian level, once you've identified them, okay? So at a very kind of pragmatic, workman-like level, to me, and scattering amplitude is a diagnostic, like anything. It's a diagnostic that lets you study and find structures that otherwise would be obscured by formalism that we know in the end will evaporate from physics. Okay, sounds like someone's driving. This leads me to the rest of my talk. So as I said, the first thing I'm going to talk about is some of what these new structures are and what I think implications they could have more generally. And I do want to say that I'm going to present here a very kind of idiosyncratic slice of all the very cool things that have been happening in scattering amplitudes. If you want to take a deep dive, you can look at last week's Zoomplitudes meeting, where there were many very interesting developments, and many of which I could list off, including, for instance, formulas that describe scattering amplitudes you can write on like a napkin, which have all orders, all endpoint amplitudes and Yang-Mills or gravity, or other formulations of QFT using the notion of a volume as describing scattering amplitudes. I'm not going to talk about any of that here. Those are very interesting. I'm going to focus on a smaller set, those which in particular involve color and kinematics. So the kind of first lesson of amplitudes that I think can tell us something maybe more broadly about QFT is that color and kinematics are dual. And just the statement of this already should sound confusing if you've never heard of it. Especially since color and kinematics are kind of things that act on completely different spaces, right? Color acts on space of, it's a kind of a discrete space, and kinematics is act on this continuous space of polarizations and momenta. But take the case of 3-point scattering. So famously in 4 dimensions, you can write down the 3-point gluon scattering amplitude and 3-point graviton scattering amplitude purely from constraints of Lorentz invariance. You can actually do this outside of 4 dimensions. You can also add masses and so on. This is all now a very old story. But if we just focus on the case of massless spin 1 and massless spin 2, then these are the formulas written in terms of spinor helicity variables. And you can just observe just right at the onset, which is that you can relate these trivially by a simple operation where you take FABC, the color a structure constant, and you just replace it with another factor of the kinematic piece. So you just take this kinematic piece and you replace FABC with another factor of that kinematic piece, and what you get is the 3-point graviton scattering amplitude. Okay, so of course the color is gone in the gravity theory because there's no color, and you've just doubled the kinematic structure. Okay, so this should not be so impressive if you know anything about how these things are fixed by Lorentz invariance, but this is the kind of first avatar of this kind of relation, and it's the basic procedure, which is find something that looks some color structure that looks like a kinematic structure and interchange them as you like. Okay. Now the kind of big development in the last decade was from Bern, Carrasco, and Johansson, who understood and realized that you could generalize this well past 3-point, 4-point, 5-point, and higher to all endpoint, and you can do that in the following way. And I'm going to consider this for the case of 4-point just to illustrate. Okay. So let's say you computed a 4-point Yang-Mills amplitude, and you wrote it in this particular form. Okay, so CS, CT, and CU are just color structures, the usual ones. And of course, they satisfy the usual Jacobi identities as an algebraic identity. Now, within NS, NT, and NU, those are just functions of the Mandelstam invariant, say pi.pj, pi.ej, ei, ej. Okay, and ST and U are just, of course, the usual the poles that we have in the amplitude. Now, you might wonder, wait, what happened to the coordinate contact term and the Yang-Mills amplitude? But the idea here is that we've absorbed that into either NS, NT, or NU. Okay. Obviously, if NS has a term that's linear in S, then I get a contact term here, and vice versa for these other 2 terms. Okay. Now, of course, the way you absorb that contact term is not unique in general. You could kind of imagine reshuffling it in different ways. And at general endpoint, there's many ways to take contact terms and reshuffle them in this way. But the kind of key insight of BC and J was that if you take an endpoint amplitude, while the color structures satisfy this identity, the numerators, if I just give you some representation, will in general not satisfy the same identity. Okay. But if you reshuffle terms, that is to say, take those local contact terms and move them around in an appropriate way, which is to say, find the right representation, you can find a representation for which this is true. Okay. And I say requires reshuffling, which I think always causes confusion. I remember when I was first hearing about this, it was confusing to me. I was like, what's the procedure? What's the mechanistic procedure by which you construct these numerators? And at this stage, there's algorithms, formulas for these numerators in various theories, including Yang-Mills. But the kind of reason why it's said so vaguely is that the shuffling is not unique. In particular, at higher point, there's many ways to reshuffle things in order to accommodate these identities. In other words, these identities do not uniquely fix the expression. Okay? But the amazing thing is that if you find such a representation, then something kind of amazing happens. Okay, so the idea is you've reshuffled terms, you've associated terms between ST and U in such a way that this is satisfied. Once you have such a form which is compliant with the Jacobi identities, then you can basically say that color and kinematics satisfy the same algebraic identities. And then the enormous leap is to just say, well, maybe they're just somehow the same. So let's swap them. Okay, let's interchange them in the case where they satisfy the same algebraic identities. So the kind of amazing, still amazing to me fact is that, let's say you take the Yang-Mills amplitude, again, highlighting the fact that NS, NT, and NU depend on a polarization vectors, E mu, and you just take the color factors and just replace them with the kinematic factors. Okay. So each of these just becomes NS squared, NT squared, and NU squared. This is called the double copy procedure. Then what you get actually is not just some random function. It turns out you get the graviton scattering amplitude. Okay. The idea is that NS squared now has 2 copies of the polarization. It has one factor of E, a second factor of E from the other factor, and those combine to form a rank 2 tensor, which you interpret as the graviton polarization vector. Okay. Now, the fact that this happens should not be obvious, right? Because if you just take numerators and square them, there's no reason the thing you get in general needs to be even gauge invariant or diffeomorphism invariant. We're not taking amplitudes and squaring them. We're taking parts of amplitudes in a certain gauge and squaring them and getting some new expression. So this is kind of the amazing, really the heart of what's amazing, at least to me. You can do kind of more exotic things. You can take what's called an asymmetric double copy, which is you could take a Yang-Mills amplitude on one side and take another Yang-Mills amplitude where its polarizations are not E, but E tilde. Okay, so I have kind of a Yang-Mills and a Yang-Mills tilde theory, each with its own separate polarizations. And you can take a copy where you take one factor from each. And if you do that, then your kind of natural rank 2 object actually is not symmetric anymore. And as it turns out, it describes a scattering amplitude for a graviton together with an antisymmetric 2 form and a dilaton, which I think not coincidentally is the zero modes of the closed string. Right, so you can kind of mix and match theories and combine them in this interesting way. Now, at this stage, long ago, double copy was proven. The fact that this gives the graviton amplitude is proven at tree level for any endpoint scattering amplitude. And it's been recycled using generalized unitarity methods to loop. Okay? And the idea behind generalized unitarity is that you basically build loop integrand ansatzes, if you like, and then you study them on cuts. And on the cuts, they have to agree with products of tree amplitudes, so you can use this to bootstrap from tree to loop. And at this stage, it's such a kind of mature field that they're, as I think many of you know, used in high order collider physics calculations. They're used in calculations at very high loop order to determine properties of finiteness of supergravities. And as I'll mention at the end of this talk, have very recently been used to perform new calculations which are relevant to the binary inspiral problem at LIGO. Now, the color kinematics duality is not just a property of gluons and gravitons. That's of course where it was originally described, but it's kind of weirdly ubiquitous. So if you have a theory that you know, which you would consider nice, which probably means it has very few coupling constants, which are fixed by, with all interactions fixed by a small set of principles, there's like a decent chance it's on this huge table from Zvi Byrne and company's review on double copy from last year, which I highly recommend. But they're kind of a couple basic elements, which I think, at least in my mind, form the backbone of what the double copy is. And those are not just gluon squared equals graviton, but some other kind of curious characters. So for instance, you can take pion amplitudes, okay? Now, of course, pions don't have color. So I'm taking this nonlinear sigma model amplitudes in the chiral, m squared equals 0 limit, so no chiral symmetry breaking. And instead of having color, you have flavor. Okay, but in the very same way that you can build amplitudes for Yang-Mills, you can build amplitudes in the nonlinear sigma model, and you can apply the exact same construction that I just mentioned before. Okay, you put them into ST and U form, you square the numerators, and when you do that, you get amplitudes in something called the special Galilean, which is a version of the Galilean theory, which has this extended shift symmetry and shows up in modified gravity and cosmology and massive gravity theories. But there's some version of it called the special Galilean, which has an enhanced symmetry beyond the usual Galilean. And it turns out these amplitudes squared give these amplitudes. You can do even more strange things. You can take a gluon amplitude and a pion amplitude. And for the gluon amplitude, you take its color structure and throw it away. For the pion amplitude, you take its flavor structure and throw it away, and then you take the product of their numerators, and you get the amplitudes in Born-Infeld theory. Okay, so this is not, the reason for this slide in part is I want to emphasize that while this double copy, of course, did arise long ago in its first vestiges in something called open string closed string duality through something called the KLT relations, they apply to theories that generally we don't think of as kind of strongly associated with string theory, in particular the special Galilean. In fact, all the Galileans are known to be inconsistent with ultraviolet UV completion because they fail positivity dispersion relations because the leading four derivative terms are actually excluded by symmetry. So these kind of theories are not usually the ones we associate with string theory. And they're also not usually the ones we associate with other types of, squaring relations like Kaluza-Klein reduction or the Vierbein formulation of gravity. The fact that these all show up, I think, is interesting, and I think could be something deep. Maybe it's not deep, I don't know. But in my view, while you can understand these as kind of mathematical statements that descend the low energy limit of string theory, you can also frame them as just QFT properties. And I just have I think we should try to understand them within QFT because they can be described as properties purely of QFTs. Okay, now maybe this is all just games with amplitudes. Maybe this is kind of just funny structures found. That's actually possible. And I think that's actually perfectly fine. These are kind of just interesting structures that scattering amplitudes have. But I think the kind of very best case scenario, which is I think totally possible, is that amplitudes are revealing real structures that are in QFT, and that these structures are by no means under the monopoly of amplitudes. Once you understand what the structure is, you could attempt any approach you like to try to understand what the structure means. Okay, the kind of greatest aspiration this could be, the example I would give is something like the Lorentz transformation, right? It's called the Lorentz transformation and not the Einstein transformation because it was discovered first as a mathematical property of equations, one which was undisputably just a true fact about Maxwell's equations, which is the Lorentz invariance, but one whose kind of physics wasn't fully put together, okay? But it was the key to something bigger, and this is my hope for this, and that's why I think at least deserves study. Regarding the kind of technical aspect of the double copy, and in particular color kinematics duality, I want to give another analogy, which is, this is a little bit like if you imagine the universe was described by 5-4 theory. Okay, imagine we lived in a 5-4 universe, but through some historical accident, it just turned out that the action that we learned from our textbooks was a field redefined action given by this, where f was a z2 violating function of phi. Okay, it just happened to be. This is the way we were handed this action. Now, of course, if you went to a collider and scattered phi particles, you'd find that they all satisfy a z2 selection rule, and you deduce that this is a property of the theory. But if you just computed amplitudes in this way, what would you find? You'd find that every single Feynman diagram would violate the Z2 on phi. But there would always be a way of reshuffling terms, moving them around in some kind of weird arbitrary way, which would restore the Z2 term by term in that Feynman diagram expansion. Okay. Now that reshuffling would not be unique because there's an infinite space of Z2 preserving functions, which are field redefinitions. But this would be a way of discovering the Z2 kind of purely at the amplitude level, which is the reshuffling process is kind of secretly finding the right representation in terms of Feynman diagrams to make that symmetry manifest. Okay, so this idea of reshuffling diagrams to manifest a symmetry is in some sense has always been around. Take any theory with a symmetry, destroy the symmetry with a field redefinition, in other words, make it not manifest, and you'll have to reshuffle diagrams to remanifest that symmetry. Okay, so that's a suspicion I have as to what the double copy is actually telling us. Now, let me actually make this a little more explicit, okay? So it's not just analogies and words. So I'm not going to be able to tell you, here is the gravity action, which is the square of the Yang-Mills action, because no one has that at endpoint. It's an open problem, and I think one that's very interesting and I'm still thinking about. But let me consider kind of a baby subset of what the double copy tells us. In particular, let's consider the asymmetric double copy I mentioned before, where again, the n's are functions of E and P, and the n tildes are functions of a polarization E tilde and P. Okay. Now, it goes without saying that n and n tilde are separately Lorentz invariants because they're just inner products of momenta. So ns and ns tilde here are separately Lorentz invariants, okay? Which means that within ns, nt, and u, I could define subscripts mu, and within ns tilde, nt tilde, and u tilde, I could input subscripts mu tilde, which have a separate Lorentz invariance. Okay. In other words, I'm saying that this representation of the amplitude has two separate Lorentz invariances which act on it, and that is highly non-trivial if you think about computing this with the standard Feynman diagram method. In other words, it's saying there's a way of taking the observable, okay, adjacent to the observable, the amplitude, and actually manifesting two Lorentz invariances. And you could ask whether you could do that at the Lagrangian level, once you know what to look for. And in fact, you can exactly do this. Can the double Lorentz invariance of the graviton scattering amplitudes be made explicit in the level of the off-shell action? And once you know what you're kind of looking for, it's actually pretty mechanical. We did this in 2016. So what are we looking for? We're looking for a way of taking h mu nu, the graviton fluctuation, and embedding it within some bigger object, which is a 2-index tensor, which is not symmetric, but has an action where the left and right indices of this not symmetric tensor have separate Lorentz invariances, 2 separate Lorentz invariances. So the way to hunt for this is to start from some standard action that we're used to, like Einstein-Hilbert plus some gauge fixing, and then apply that arbitrary field redefinition. So we can take a completely general gauge fixing, local gauge fixing, I should say, and we can take a completely general local field redefinition. Usually when we do graviton perturbation theory, we just write down the first 2 terms here, but under a field redefinition, I can add any set of corrections, and you just add anything you like here with free coefficients. And then you fix those coefficients in order to try to manifest this property of a doubled Lorentz invariance. And yada, 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 you can do this and you get the following, I think, remarkably compact action for the scattering of gravitons, 2 forms, and dilitons. So the idea here is that capital H is comprised of what we kind of normally think of as the usual graviton, but I've extended the kind of number of dimensions that the indices run over from D to D plus D, so that is to say 2D. And I have derivatives which act on the 2D dimensional space, but in some sense, there's still just one coordinate, x. There's still just the D dimensions, but I'm repackaging it so you can see how the Lorentz indices contract in a way that no barred tilted index will contract with a non-tilted index. And it's kind of cool because this also has kind of nonlinear sigma 1 form to it. So this is a very compact way of writing down pure gravity action. So it's compact, but it also has this doubled invariance. And if you, by construction, look at the off-shell Feynman diagrams, they literally have 2 Lorentz invariances. Every Feynman diagram has 2 separate Lorentz invariances which act on it. And if you compute the on-shell amplitudes, they have a doubled gauge symmetry. So this is a baby example where just the global symmetry part of the scattering amplitude is something you can eventually ultimately reverse engineer at the level of the action. And I think it's clearly deserving of study to see whether you could input the whole gauge symmetry into an action of this type. Okay, so that's one of the first lessons I want to mention. The second lesson I want to mention is something definitely continuously connected to the double copy, but kind of a slightly different character, which is that secretly gravity is the mother of all theories. Okay, so all the theories I mentioned before, like the special Galilean, nonlinear sigma model, Yang-Mills, Born-Infeld, it turns out they're all unified, in a sense, under gravity in the following explicit way. Okay, imagine that an oracle who knew all the S matrices just handed you the full graviton S matrix. In fact, they only did hand you the graviton S matrix at tree level. Okay, they give you every endpoint scattering amplitude in gravity. It turns out that from that big giant mathematical object, you can sculpt out from it in a super mechanical way all the amplitudes in every other theory, gluons, pions, Galileans, and so on. Okay, these are all secretly hiding inside gravity. And in this sense, they're unified in a particular way. Now, I want to emphasize here that this sense of unification is totally different from the usual picture we have of unification in high energy physics, where we have some unified group where symmetry is restored. At low energies, there's symmetry breaking, and then we get some smaller symmetry group where it's going from low energy to high energy. This is not a statement about energies. I'm not saying that pions come from some condensation of gravitons per se. This vertical axis here is spin. Okay? And the idea is that if I give you a graviton scattering amplitude where they're scattering each other at 5 GeV energy, then there's a way of converting that amplitude into a Galilean amplitude that's scattering at 5 GeV, okay, at the same energies. Okay? And let me just show you what the mechanics of it is and see what it can teach us actually about Lagrangians. Okay? So we're going to kind of compute an amplitude in a standard way. If you like, you could use your rules from Peskin and Schroeder and just compute a scattering amplitude. And what you'd do is you'd build this function A for an endpoint function and dot it into polarization vectors. And obviously A is just a scalar function of these Mandelstam invariants. So this is a Yang-Mills amplitude here. Okay. Now, the idea of this is we're going to take A and think of it as an abstract function of these invariants. Okay, it's a scalar function of a bunch of scalar objects. and then just study its properties. Okay? Now, of course, we have to maintain on-shell conditions. Nothing will make sense if we go off-shell, so we have to constrain that certain combinations of these variables that this can depend on are actually 0. Okay, so let's say we do that. Now, of course, we know that an amplitude has to satisfy certain consistency conditions. I was telling you before how this causes redundancy, but I've committed to having polarizations here, so let me just commit to it. And with polarizations, we have to introduce a ward identity, which is a statement, of course, that if you take a polarization and replace it with a momentum, then you get 0. Now, we can recast this ward identity as a differential operator. That differential operator, I call it Wi, simply says to differentiate with respect to any Mandel-Stam invariant involving EI, and then replace it with PI dotted into that Mandel-Stam invariant. Okay, so you can convince yourself that Wi is literally just a differential operator that applies this ward identity to this amplitude. So what we say is that this differential operator Wi annihilates the amplitude. It's just a very formal way of writing down the ward identity. Now there's another constraint that amplitudes satisfy, which is momentum conservation. And this seems trivial, but here I'm going to institute it as an operator statement. And we can write down an operator, which is basically any vector dotted into the sum over all momenta. And that, when it acts on an amplitude, should also be 0. Okay, so the idea is that this is another operator which annihilates the amplitude. Now, the kind of advantage of just formally constructing a Wi and a P is that we can now build a new operator called T, which stands for transmutation. And the purpose of T is that it acts on amplitudes A to produce a new object, T times A. And T is specifically constructed so that it commutes with the ward identity and it commutes with momentum conservation. And you can see that once you build such an object, then you're guaranteed that if A is gauge invariant and momentum conserving, then so too is T times A. Okay, so this takes gauge invariant momentum conserving objects and makes new ones. Now, that is not a sufficient condition to make a new scattering amplitude. Obviously, just because something is momentum conserving and gauge invariant doesn't make it anything physical. I could take a Yang-Mills amplitude and take its 17th power, and that's gauge invariant and momentum conserving, but it's nothing. Okay, it's just some random function. But the kind of amazing thing is that if you take these transmutation operators, which are shown here, they literally just take you from amplitude to other amplitude. Okay, so I'm being very explicit. These are the exact full differential operators involved. And they have a certain action which converts state to state. Okay, so if I give you a Yang-Mills amplitude and I act with these, then they convert gluons to scalars. And here by scalars, you can think of them as let's say scalars, say a scalar QED, which I'll show you a bit shortly. Or you could reduce it to a different kind of scalar, which is one which is more like a pion, okay, which is the pion. Okay, so by repeatedly applying these operations, we can go from Yang-Mills amplitudes to amplitudes in phi cube theory or the chiral Lagrangian. Okay, and this is not a speculation. You can just prove that this is true for all graviton, gluon, and pion tree amplitudes, and you can also go through explicit checks. But it's actually just kind of cute. You can just take Yang-Mills expressions from your textbook and hit them with these objects to get other amplitudes. Okay, so it's not trivial that this worked out, as I said previously, but let me show you how it works in some examples. Okay, and the simplest example is so trivial that it shouldn't even really get a name. This is a trick that people have used in amplitudes forever, not even amplitudes, but just everywhere, which is to go from Yang-Mills to say scalar QED. Okay, so let's say I give you a gluon amplitude, A, G1, G2, G3, G4, so these are 4 gluons. And then I apply this differential operator, T1, 2, T3, 4, which is just this. What do you get? You get this amplitude here, P1, P3 over P1, P2, which is, you'll recognize exactly the amplitude for scalars interacting, charged scalars interacting through exchange of a photon. Okay. Now, the reason why this is not impressive is that it's literally the same as dimensional reduction. Okay. When I extract out the E1.E2 piece and the E3.E4 piece, all I'm doing is basically picking out the E1.E2 and E3.E4 terms, and that's identical to dimensional reduction. Okay, so here it's the same as taking E1 and E2 and essentially polarizing them in extra dimension. Okay, oops, extra dimension. So actually, I'm hearing this bird here. Let me move this just so it's out of the way, in case it's too loud. This is the problem with living in California. Sorry about that. The idea here is that E1 and E2 you can think of as polarized in their own separate extra dimension, and E3 and E4 are polarized in their other separate extra dimension. And then we see that the scattering is just A5s scattering against A6s. Okay, so this is just a rewriting of dimensional reduction. Now I mentioned this kind of trivial example because it shows you how the amplitude statement can be kind of bootstrapped back up to a very explicit Lagrangian statement, right? I can of course get the scalar QED action directly from Yang-Mills by doing a D plus 2 dimensional reduction of this higher dimensional theory. Okay, now let's go to the case of Yang-Mills to pions, which I think is much more interesting. You can take the gluon amplitude and hit it with a set of differential operators here. I'm not going to write them fully explicitly here, but then you get the amplitudes for pions. Okay? And this should seem very confusing to you because pions, of course, have no color, gluons have color. But the point here is that the color stripped Yang-Mills amplitude after applying this differential operator gives you the flavor stripped pion amplitude in this case. And what is cool is you can do the same trick, kind of with the insight that this is previous case was exactly dimensional reduction. You can ask, what is this differential operation equivalent to in terms of dimensional reduction? And what it tells you is that it's equivalent to this choice of polarizations in an even higher dimensional space. Okay. The idea here is that E1 and E2, E1, E2 in E3 and E4. Sorry, I have a typo here. This should be E3 and this should be E1 and E4. I'm sorry. Those are polarized in a private extra dimension, while the other two legs are polarized in a very peculiar way. Okay. The idea here is that the first D-dimensional component here is where all the spatial momentum live. The 1 and D extra dimensional components you should think of as extra dimensions. But the idea is that if you take these gluons and polarize them in this very peculiar way, where the extra dimensional polarizations are actually proportional to their lower dimensional momentum, then that's exactly equivalent to this procedure. And what that does is it tells you exactly what the dimensional reduction is. Okay? And the scattering statement is that pions can be thought of, D-dimensional pions are equivalent to 2D plus 1 dimensional gluons that are being scattered in a very peculiar way. Now we can take that peculiar set of polarization vectors and reverse engineer their dimensional reduction. And it tells us that the nonlinear sigma model in 2 dimensions is just some exotic dimensional reduction of 2D plus 1 dimensional Yang-Mills under this transformation, okay? Where the X, Y, and Z fields are essentially parameterizing these polarizations E1, E2, E3, and E4. Okay, so again, I won't go into the precise details of how this is, but you can kind of see mechanically how X, Y, and Z mirror the structure of these polarizations. And the idea is you just take 2D plus 1 dimensional Yang-Mills and insert this basis. And what you find is that in terms of these X, Y, and Z fields, you can compute the pion amplitudes. So the pion amplitude, the amplitude for n pions is given by an amplitude with 2 Y particles and the rest being Z particles, which are longitudinally polarized, as it turns out. Now, what's most striking about this way of describing things, at least in my mind, is the fact that Bose symmetry is not manifest, okay? In this way of thinking about the action, these X, Y, and Z fields all represent the pion. The pion is not represented by one individual field. And in every other formulation of local actions I'm aware of, at least most of them, Bose symmetry is a manifest, manifestly explicit at the action level. Here it's not. In fact, let me show you what the action is. You take the Yang-Mills action in 2D plus 1 dimensions with some gauge fixing, which I think is we take gross nouveau gauge fixing, and then you just apply this dimensional reduction I just mentioned at the action level, and you get this action, which is the action for the nonlinear sigma model. Okay, and it looks very bizarre. It looks nothing like du dagger du. Okay, first of all, it does not have an infinite series of higher order operators. Pi to the 4, pi to the 6, pi to the 8, and so on. It truncates at cubic order. That's what I'm saying. It also doesn't have G parity, right? Obviously, it's not Z2 invariant, which means that the Feynman diagrams have odd point vertices. Despite that, if you string together those odd point vertices and compute on-shell amplitudes, all the odd point amplitudes vanish, and you get exactly the scattering amplitudes of the nonlinear sigma model. Now, this action actually I wrote down with Josh and Shen actually years before even this work for a completely different reason. And the reason was that we took pion amplitudes and we put them in the double copy form. We put them in a form such that the numerator satisfied these Jacobi relations. And then what we did was ask, what is the Feynman diagram expansion which produces these amplitudes? In other words, we reverse engineered an action whose Feynman diagrams gave the color kinematic dual forms. And this is the action that we had found. It's purely cubic as required. And as it turns out, the kinematic algebra is a literal Z2 symmetry of this action. So what I'm telling you is that if you take this action and take the flavor structures and you just replace them with the kinematic structures, just at the action level, the off-shell action level, you get a new action, which looks like this. You can even see how it looks like the square, which is actually exactly the action, exactly an action which describes the special Galilean. So this is a new form for the special Galilean action, which amusingly also is not even dimensionally dependent, unlike most gram determinant type forms of the Galilean. Yeah. So in this sense, the kinematic algebra is an explicit symmetry of the off-shell action. And in fact, there's some slight insight we get into what the kinematic algebra is, which is that it actually descends from the higher dimensional Poincare algebra in this example. Okay. So this is an example I want to give where we don't just kind of say words, but we can make direct contact. This duality between, in this case, flavor and kinematics is just a symmetry of the action. Sadly, such a thing has not yet been achieved for Yang-Mills and gravity. That's still an open question, and I think we would learn something from it. So yeah, I kind of said these already, but to recap this kind of interesting nonlinear sigma model action, the interactions are all purely cubic. Bow symmetry is obscured. The kinematic algebra comes from the higher dimensional Poincare algebra. And maybe the last thing I'll mention is that the soft theorems of the gluons all map onto Adler zeros of the pions. In fact, all the leading and subleading soft theorems that have had some attention in recent years, they all are mapped onto each other through this dimensional production. Okay, so that's all I want to say about Lagrangians. I do want to mention maybe some more recent work trying to do something slightly more ambitious, actually, which is to not just lift the gauge squared equals gravity statement from amplitudes to Lagrangians, but to even consider the possibility that it may be a state mapping. Okay, so this is something that you might expect from open string closed string duality directly, because open strings, there's a duality there. But one could dream of having not just gluon amplitude squared equals graviton amplitude, but that the gluon state squared equals a graviton state. So these here would be Hilbert space kets in the graviton effective field theory, and these would be gluon kets in the Yang-Mills squared theory. And there's a question of whether you could build the state mapping. Now, if you could build a state mapping, this would be unbelievably powerful, I think, because it would give you a weak dual description of any gravity setup. Basically, take some setup you're interested in gravity. Let's say a bunch of medium energy gravitons coming in, forming some state, let's say a black hole, which then decays into thermal radiation. Okay, but you can describe this as an amplitude statement because it's in states and out states. If you could characterize this as kets scattering in and then ending in some final state, then you could transform that into a gluon question and then attempt to make progress. Okay. So this is obviously a fantasy at this stage, but there could be some potential in trying to actually build this mapping explicitly to deep problems in physics and even maybe going to finite coupling for the double copy. Okay. But let me just tell you what we did. This was recently a couple of months ago, which is just, let's write down a twin gauge theory, Yang-Mills cross Yang-Mills bar, where both factors have an SUN gauge group and there's just no gravity in the whole setup. Okay. Now here's the question. Can I build an entangled superposition of gluons which scatters just like they were gravitons? Okay. Can I fake gravity by just taking superpositions of gluons? And there's some technical reasons why you can't just read this off directly from KLT or BCJ, which I won't get into, but you can just write down such a state. Okay. So here's a ket from one Yang-Mills factor, here's a ket from another Yang-Mills factor, and then here's some set of coefficients which define the entangled superposition. And I want to define that as some new state, which I want to behave just like a graviton state. And there's some some constraints on the superposition given dimensional analysis and some assumptions that are, I would say, mostly aesthetic. And then some assumptions which are required, like the fact that this thing should be permutation invariant. But the kind of ultimate point is that you can do this exercise at 3, 4, and 5 point. And what we found was that at 3 point and 4 point, essentially any arbitrary collection of entangled gluons subject to these assumptions just scatters exactly like gravitons. And a kind of corollary to that is that entangled pions pions which are entangled in exactly the same way are exactly the same as Galileans. So if you scatter them, they just look just like, their scattering amplitudes are precisely the same as those of Galileans. At 5 point and higher, just simply entangling them isn't good enough, and you need other constraints, some of which are relatively modest. But we, at this stage, we don't fully understand what this means. We haven't gone to 6 point or higher. We don't know whether this is a deep thing or just some triviality. I don't know personally. One thing I should say is that, of course, the natural thing to do is to look at the density matrix for the state and trace out half the Yang-Mills. And not surprisingly, the state is maximally mixed at large. Again, I wouldn't read too much into that. That's actually obvious given just the structure of the ansatz. But I think this is maybe another approach, which is to try to think about this in terms of states and in quantum mechanics rather than at the level of the Lagrangian. Okay? And I can tell you more about that, but let me put that aside. So at the end of the day, these are just some really just modest developments trying to understand some things outside of the usual just straight up compute scattering amplitudes program. And there's a lot of just unanswered questions, which is, one, can we explain these structures? And explain is kind of a loaded word. I mean, mathematically, they're factually just true. There's tons of mathematical arguments. And within the language of scattering amplitudes, there's many ways of understanding them in physical senses. But there's, as of yet, not like a symmetry argument, like a physical symmetry argument that I could explain to someone outside of amplitudes, which is what I think would be the grand goal, the highest aspiration of actually communicating things. It's not required that it should exist, but I think it's something worthy to attempt to find. A more modest goal is to try to just exhibit some of these properties at the action level, and I've showed you some things where we can do that, but we still do not have gravity as gauge squared at action level. We don't have color kinematics for all of these theories as an optional symmetry. I think this could offer insight into the structures residing within these old classic theories like gravity and Yang-Mills. So I think that's an interesting question still. And then the last thing is kind of what I want to end with, which is, can we use any of this for anything? Can we recast hard gravity problems in terms of gauge theory? And I want to now consider kind of an application. And I have to mention this very cool fact, which was discovered by O'Connell and Montero, which is the so-called classical double copy, which is that there seems to be some kind of avatar of the double copy at the level of solutions to classical equations of motion. In particular, you can take the Schwarzschild metric and write it in the Kerr-Shield gauge, which is this form, where, as it turns out, this k nu and k nu is literally just the gauge vector for a monopole, electric or magnetic monopole in the gauge theory. Okay? So this is like the double copy at equations of motion level. I should say it's not currently understood how or whether this is continuously connected to the full perturbative double copy I mentioned before, but it's extremely enticing. And if you don't know anything about Kerr-Shield metrics, it's just really cool classical field theory. Let me just mention one thing which is fascinating about it, which is that usually when we talk about classical solutions, we know that they're secretly generating functionals for tree amplitudes, right? If you solve the equations of motion in the presence of a source, it's literally the generating function for all tree amplitudes, which is why if you look at the Schwarzschild metric in its usual form, there's like a G piece, a G squared, G cubed, G to the fourth. And you can look at each of those terms and they correspond precisely to higher order tree diagrams with more and more insertions of a heavy source. But the Kerr-Shield solution is fascinating because it only has 1 power of G. So it's some kind of representation of Feynman diagrams where that whole space of many, many higher order nonlinearities in gravity are just resummed into a simple, kind of Born exchange. So it's actually pretty interesting. But in any case, it's kind of separate from the story. In recent years, a large fraction of the amplitudes field has kind of mobilized to attempt to make real direct connection to gravitational wave physics. Not just at this interesting level of classical solutions, but for the case of real kind of in-spiraling black holes, which is the thing I want to talk about in the last, I guess, 10 minutes I have, maybe. Let me try to be fast. So as you all know, the binary black hole merger has multiple phases. There's the in-spiral, the merger, and the ring down. The merger, of course, is strong field and not amenable to perturbation theory. The initial in-spiral phase is amenable to field theory because it's, in some sense, kind of obviously weakly coupled. The black holes are distant from each other. And there's a whole field of post-Newtonian perturbation theory that's decades old, which is what people have studied. And that's what scattering amplitudes has been focused on as of late. Now, of course, you might ask, why don't you just put the whole thing on a computer and just do numerical relativity from start to finish? But my understanding is that it's extremely cost inefficient. It honestly just takes too many cycles to just run this thing in a circle for ages. And the cost is prohibitive because a priori, if you have some event in the sky, you don't know the parameters of the thing you're scattering, the thing the black hole's orbiting. So it's too costly to just run this. So what the reason this kind of field exists is that it allows you to do analytic calculations kind of as far as you can, and then kind of merge this continuously to the merger and then the ring down phase. So the ultimate waveforms that we see in the data is kind of a merging of these three different regimes so that they can run these things and study the new physics in kind of a prompt way. So it's just prohibitive to just do this all on the computer. Now, the kind of standard post-Newtonian expansion is in velocity squared and gm over r, which are the same in the virial limit. And that's the usual expansion. But there's another expansion, which is called post-Minkowskian, which is just the expansion in g. And in quantum field theory, we just call this perturbation theory. It's expansion in the coupling. And the kind of key point here, if I just zoom out a bit, is that from a relativistic point of view, it's unwise generally to expand in velocity squared because relativity fixes those coefficients relative to static pieces, right? Relativity is extremely constraining. So if you take your theory and break it down to the post-Newtonian limit, then you break that symmetry and you can lose things. And the idea of applying scattering amplitudes is to keep everything, keep as much as you can in the velocity expansion until the very end, and then compute everything at all orders in velocity and at some order in g. And we can draw a map of perturbation theory. I think as of maybe a year and a half ago, prior to a year and a half ago, this is what the phase diagram looked like. The green here is kind of standard post-Newtonian, and there were some post-Minkowskian calculations that had been done here and there. Now, the first thing you would worry about, which hopefully I've disabused you of these misconceptions in this talk, is, well, hold on, amplitudes can't do anything because black holes are much different from super Yang-Mills n equals to 4. But that's just at this stage, completely an obsolete notion. Double copy, on-shell recursion, the bootstrap, all these things can be applied to masses, and the proof's in the pudding because we applied them for massive black holes scattering in minimal Einstein gravity, which I'll tell you about. But this is not something that we worry about because amplitudes applies to a huge class of theories, including massive states interacting through Einstein gravity. The other issue is that LIGO doesn't observe scattering. You can compute a scattering amplitude all day, but they don't measure that. But that's fine also because NRQCD solved this problem ages ago. You can, of course, compute scattering amplitudes and doing a matching calculation to extract a non-relativistic potential between two bodies. So this has been a solved problem. We just had to adapt it slightly to this new context. So all these puzzles have actually been surmounted, and there's very quickly, swiftly appearing results, some older from years ago, like conservative dynamics, and new ones that should be forthcoming on spin and finite size effects and so on. I'll just say this in one line. Basically, the idea here is that we compute the amplitude using newfangled amplitudes tricks. We also compute the amplitude in an effective field theory, like an NRQCD, which is trivial because the Feynman diagrams are all trivial. We match them, and then we use the matching calculation to extract the Hamiltonian of the system. And extracting all the amplitudes is trivial using double copy and using all these different transmutation tricks I mentioned before. It's literally a set of differential operators and replacements to extract the tree amplitudes relevant to this process. The upshot is that I guess in 2018 and 2019, that was a while ago, we computed these rows, keeping in mind that these go off to infinity because we're doing post-Minkowski. And the fact that we have covered a white region here means that this is now the state of the art in terms of the post-Minkowskian expression. This is the amplitudes calculation is the leading expression in this direction, not in the post-Newtonian direction, but in this direction here. And the existing community is diligently, I think, checking our work and have verified that this term and this term are correct, and they're going to keep, I guess, working their way up until they reach infinity. So one thing I should mention is that our next task, of course, is to eventually subsume all of these and my personal view is just given the strength of calculation ability amongst people in amplitudes that these will be covered in some time. Okay. Here's the answer, just to make sure, to convey that we're adults and we know what we're doing. This is the full answer. It's not necessarily that pretty, but that's what the real world looks like. And just the last slide, I want to emphasize that this is not just some theorist abstraction. This here is the Hamiltonian that describes the binary inspiral for two black holes in Einstein gravity. The reason we computed it was because we were asked and motivated by LIGO theorists who said this information would be useful. Right after our paper, they incorporated it into their pipeline for effective one body and studied it relative to other approximations and to numerical relativity. So it was taken seriously enough to be put into this machine to be studied. I should say at present, I don't know if this is going to be a game changer at all for LIGO. In fact, these are higher order calculations. They may or may not, but that's not my job to determine that. These folks have asked us to do it. It's not too hard. We did these calculations in I think a span of 6 months. So we're just going to do it and provide what we can to those experiments. And I think there's a big future ahead for computing this, not even in the context of just pure gravity, but let's say with massive gravity, with extensions, with other states involved, so on and so forth. Anyways, here are my conclusions. I think I'm running probably a little late, so let me not go through them explicitly, but just say I think that scattering amplitudes has already revealed new structures lurking inside classic old theories that describe the world we live in. And I don't think that you need to just study scattering amplitudes to try to understand them. I think you can attempt to attack the question of what these structures mean purely from the point of view of symmetries and actions once you kind of know what to look for. And a lot of these kind of new tools, we've been able to use them now to an altogether different physics problem, which is gravitational wave physics. And I think that's all I want to say. And let me thank you for your attention. That's it.
Okay. Thank you very much on behalf of the audience for this very beautiful talk. So, questions?
I do have a question, Clifford. So you argued essentially that from the looking at the hierarchy of double copy relations, so gravity and then spin one and so on, you argue that they descend from each other via dimensional reduction. And this sounds very plausible, basically. Now, the question is that, to understand if this is just an accident or if something deeper, the question is that, is there anything similar for fermions, involving fermions? Because clearly, if you see where I want to go, right?
Right. I think that's a great question. I've been asked that before. It seems extremely natural, especially given I should have mentioned that all these double copy, I didn't even say this, but the double copy relations can all be dressed with varying amounts of fermions. So for instance, if you take the fermionic analog of some of these examples, you can take, let me try to remember which one it is. The double copy of, I forget which fermionic derivative, nonlinear sigma model. Yeah, nonlinear sigma model and the gauginos of supersymmetric Yang-Mills. And that double copy is VA theory. Okay, the effective field theory for Goldsteinos. So all of these, I forget which or where, they have kind of a double copy that exists for the fermionic case. The kind of technical obstruction to writing down like explicit dimensional reduction is just the usual annoyance of fermions. Given that their dependence on dimension is a little particular, right? So it's hard for me to write down just a representation in abstract 1 plus 2D dimensions for the fermion and then reduce. I haven't attempted it. I think it could in principle be doable. But I think it's a technical challenge.
Okay, that was exactly my question, right? Because of fermions is more complicated. So has it been done in particular cases? I'm not saying, let's say, in
no, it hasn't. It hasn't been done, and I don't think it would be crazy to try to just do it. So, for instance, you could take Yang-Mills in some 2D plus 1 dimensional case, and just write down the explicit fermion representations and just try to do it. Probably the best approach would be to just supersymmetrize the whole thing and then dimensionally reduce the supersymmetrization. That's what I would do, but it has not been attempted as far as I know.
Okay, thanks.
I could be wrong. Yeah.
Good. More questions?
Can I ask another question? Yeah,
Sure.
so great talk. My question is, what about double field theory? Does it have any role to play here?
Good. You know, this double, I should have mentioned this, but the double Lorentz invariant action, it's actually a field redefinition of the double field theory action. This double copy gravity action, and that comes from some compactification on OD comma D space. I've wondered whether you could draw a direct connection, and I've actually attempted to make such connection, but it's not, at least to me, obvious why there's two explicit copies. And this certainly hasn't been expressed, as far as I know, in terms of a literal action level. I think one thing that might be cool is to take the double field theory actions and transmute them in this way and try to build double field theory for like pions. I think that's definitely enticing. And in fact, I think that's probably a more likely avenue for insight than Kaluza-Klein reduction or even Vierbeins. So yeah, I think that's an interesting question. I haven't continued to pursue that since we wrote that paper a long time ago.
Right. Cool. Thanks.
Sure.
Other questions from the audience?
Maybe I have one.
Please, Diego.
Hi. Yes. Can you comment on the role of Lorentz invariance in all these relations? So, because in principle, you could try to use this machinery for non-relativistic theories or condensed matter. Who knows?
Yes. So that's something I'm actually thinking about now on a number of different fronts. But there's kind of two aspects of amplitudes. Okay, so one aspect is new structures, so things like the double copy. And there just literally has been, like, as far as I know, no work on studying whether there's a double copy for a non-relativistic system, which I think is a shame. And I think one should look for one. And I don't think it's all crazy that you could try to build one. Obviously, there's a whole zoo of condensed matter systems. The kind of crucial point is that Lorentz invariance is very constraining. So in general, if you have less than Lorentz invariance, you'll have Galilean invariance or some Schrodinger symmetry or some subset of a bigger symmetry that we're used to. Then you will have kind of more free parameters. But that doesn't prevent you from trying to study the amplitudes and see if you can construct a double copy. Now, there's another aspect of amplitudes, which is not finding new structure, but just kind of classifying. So one thing that we had studied a while ago was using soft limits to basically classify these effective field theories. And DBI and Galilean all show up as things that have nice enhanced soft properties, infrared properties. You could use exactly the same classification to study non-relativistic theories. And then the kind of phase space of theories will be much more rich, actually, because there's less symmetry, because there isn't the full Lorentz symmetry. So I think we're actually thinking about that now. I think it's still an interesting question to try to understand that. But Lorentz invariance is not crucially essential to anything in terms of studying the amplitudes and trying to bootstrap them. It might be essential to the new structures found, but we don't know because there's been so little like kind of exploration outside of this relatively small window of field theories, which is relativistic QFTs. Yeah.
Thank you.
Other questions or curiosities?
Maybe curiosity.
Please, Roberto.
I think I've lost part of your talk, so you may already have answered to that. But is this a good way one could think to build higher spin theories? You are going up and down, apparently, going from graviton back to pions. So is there a way even higher spin in this direction?
Good. So regarding the transmutation, which was like an operation which reduces spin, you can't get higher spin. But you could ask, can you build a double copy by taking states with even higher spin and gluing them together to get even higher spin theories? And what's kind of amazing is that, well, first you need to write down a greater than spin 1 theory with color, okay? But if you just take kind of the representations that exist for doing double copy in a very clean, simple way, like the CHY scattering equations, and you just try to pair together theories to get higher spin theories, you get inconsistencies in the sense that in the case of just at a technical level, you just see that the amplitudes don't make any sense. This is kind of clear because people have studied if you take, for instance, BCFW, and you take higher spin 3-point amplitudes of massless states, and you just string them together. And what you find is that these amplitudes don't factorize properly. Essentially, Bose symmetry, which would enforce the idea that you could do so-called BCFW recursion in different channels and get the same answer, is violated. Okay, so it's kind of a way of diagnosing that these higher spin theories are actually sick. There's a number of different ways of doing this. You can also just be more direct and just write down an ansatz for a higher spin theory and demand that it satisfies, that it has a stress tensor, and that it can couple to gravity, is local Lorentz invariant, and you can just rule it out. Okay, so there's a whole side of this I didn't mention, which is the kind of really bare bones bootstrap and see what theories exist approach. And in that case, you can, this is long known, you can exclude higher spin, massless higher spin theories in this way, just by building the function space that would coincide with its amplitude and then showing that it's inconsistent with factorization and having a coupling to graviton. So you can, and I think the answer is largely negative, to try to build such states, build such theories.
Thank you.
Sure.
Other questions? I have just a very stupid curiosity about your last part of the talk. So suppose that you have 2 neutron stars instead of black holes. So at some point in the post-Newtonian expansion, some fundamental difference should emerge related to tidal deformabilities or things like this. So
absolutely.
Do you think that you can also capture these kind of things with your techniques?
Absolutely. In fact, well, we have a paper that will be forthcoming in I would say, yeah, relatively short time scale, where we include the leading finite tidal effects for the binary inspiral and its evolution. And the idea is to just think like an effective field theorist. And so this is not even this is just a well-known thing in the community, which is that we're using quantum field theory to describe black holes, which is only true if they're completely point-like. But of course, we have finite size effects from neutron stars, and you can incorporate them as essentially higher dimension operators in the effective field theory. So these gravito and magnetic tidal effects are literally just non-minimal couplings to gravity that you add to the action. And this is well known when you study world line formalism. These are things like the so-called love numbers, which vanish for black holes but are non-zero for neutron stars. And in this picture, you just add them and do the same calculation. And the calculation isn't much harder, which is why we're doing that. So you can absolutely keep adding more and more terms. And of course, it eventually breaks down once perturbation theory breaks down because they're merged, but then you shouldn't be using perturbation theory anyway. So the idea is that, indeed, for the case of neutron stars, we want to use this for the initial in-spiral, but be able to account for those leading effects. And it's a really good question because, of course, one of the major physics cases for LIGO and gravitational waves is, determining the softness of the equation of standard neutron stars, and we need information about the finite size effects. So it's actually pretty important, I think, to include those, and they're absolutely mechanically can be incorporated using these methods because we did it, because we're doing it. Yeah.
Thanks. Super.
Sure.
Questions or final comments? Maybe. Can you see the chat, Cliff? There is a question.
Oh yeah, I think I just saw that. So, what is expected of the gauge symmetry of such a Yang-Mills squared Yang-Mills squared gravity action? Oh yeah. So what would this even look like? Okay. So what this would look like is a quantum field theory, like again, in the most pristine, beautifully packaged way. It would be a quantum field theory involving a rank 2 tensor with 2 indices. And the action would be doubly Lorentz invariant and would also be invariant under diffeomorphisms, where you shift by d mu xi nu and also by d nu xi mu bar, like 2 separate diffeomorphisms for the left and right indices. And you would just have 2 separate gauge invariances. That's what such an action would look like. The symmetric subgroup of the gauge symmetry would be standard gravity diffeomorphism. That's an example. I don't know if that's the form it would take. It's also possible that an action isn't possible and that something else needs to be attempted. For the case of pions, I think the fact that we had to essentially break manifest Bose symmetry suggests that something pretty intense has to happen. I didn't mention this, but the Plion Lagrangian we wrote down is not some trivial field redefinition of the usual du dagger du chiral Lagrangian. It's obviously much different because the degrees of freedom are not even the same. It breaks bow symmetry. So I think most likely something more drastic is needed, if it even exists. But the dream action would be what I said just earlier.
Okay, thanks. I think we can close the session. So I thank you again for this fantastic talk, Cliff.
Cool. Happy to be here. Thanks.
See you guys next week. We'll discuss the Wolfram model. Bye.
Cool. Thanks.
Ciao.
Everyone be safe.
Bye.